From here on, we will be ignoring work for the most part because it is small and focusing on the heat of a reaction. So we will look at a generic reaction, A plus B going to C, and we'll talk about the heat of reaction. We'll write it as delta H sub-reaction, and that's equal to the enthalpy of the products minus the enthalpy of the reactants. And when the reactants are lower in enthalpy than the products, then the reaction causes an increase in enthalpy, which means delta H is positive, and that is a situation we call endothermic. The reverse can happen where the reactants are higher in enthalpy than the products. So we have a decrease in enthalpy when the reaction occurs, and so that's a negative delta H, and we call that exothermic. So here are some examples with numbers. Let's say we have a reactant P going to a product Q, and the delta H for that is a positive 300 kilojoules. That means we could draw an enthalpy diagram, meaning in enthalpy going up, where P would be lower in enthalpy than Q, and the difference would be 300 kilojoules. We can look at another reaction, which is another generic R going to something we'll call S, and the delta H for that is a negative 300. So that would be a situation in which R is higher in enthalpy than S, and when the reaction occurs, you go down 300 kilojoules. All right, so let's have you try this question. Use this reaction with an associated delta H and say what the signs are for Q and W. Okay, so Q, you may recall at constant pressure, Q is equal to delta H. Okay, so delta H is over here, it's positive. Okay, so if it's positive, then Q is positive. Work, you may recall, was minus P delta V, and we did say we were going to not look at work much more, but I wanted to remind you of it. You have 2 moles of gas, another mole of gas, so 3 moles of gas in the reactants going to 4 in the products. So that's an increase in gas, which means delta V is positive, which means W is negative. So we have Q positive and W negative. Now let's look at phase changes and how enthalpy changes when a phase changes. For any particular compound, we can write an enthalpy diagram where enthalpy increases as you go up. The solid will always have the lowest enthalpy, liquid will have a higher enthalpy, and gas will have a higher enthalpy, and the gap between liquid and gas will be greater than the gap between solid and liquid. And we can talk about phase changes. When you change phases from a solid to a liquid, that's going this way, and that is known as melting. M. When you go from a liquid to a gas, that is known as vaporization, which I'm going to mark as V. And when you go directly from the solid all up to the gas without passing through a liquid, that is known as subliming, S. Alright, so melting is from a solid to a liquid, vaporizing is from a liquid to a gas, and subliming is from a solid directly to a gas. We have special delta H values we assign to those. We call the first one delta H of fusion, FUS, delta H sub FUS. When you vaporize something, that's delta H vape. And when you sublime, it's delta H of sublimation. But you can do the opposite processes. You can also go down from a gas to a liquid, and that is condensing. You can go down from a liquid to a solid, that would be freezing it. And you can go directly from a gas to a solid, that is known as deposition. Now notice those arrows all go down. The last 3 go down, the first 3 went up. The first 3 are all positive. delta H values. So whenever you go from a solid to a liquid, or a liquid to a gas, or a solid to a gas, you're going up arrows, it's a positive delta H. When you are condensing, that was our C, and condensing was going from a gas to a liquid. Freezing was going from a liquid to a solid, and deposition is going from a gas to a solid directly. And so, since they have the same energy gaps, going from a solid to a liquid is the same as a liquid from a solid, except the sign of delta H. It just changes in sign. So we can say condensing is just the opposite of vaporizing, so its delta H is negative of whatever the heat of vaporization is. And the freezing is just negative of the delta H of fusion. And deposition is the negative of the delta H of sublimation. So these three are all negative delta H values. They're all exothermic. And the first three were all endothermic. All right, and we can use delta H of reaction to calculate an amount of heat that was exchanged whenever we have a reaction. So here's another generic reaction. 2 A's, 7 B's, and a C make 3 D's and an E, and I've assigned an arbitrary delta H reaction of negative 200 kilojoules. And you should notice right away it's negative. That means it's exothermic. Okay, so how do we interpret that? This delta H, when it's written with a reaction, applies to this reaction exactly as it's written. In other words, 200 kilojoules of heat are released, and the reason I say released is because it's exothermic. If it was a positive 200, it would be absorbed. 200 kilojoules would be absorbed, but this one's released. So 200 kilojoules of heat are released when 2 moles of A react with 7 moles of B and 1 mole of C to form 3 moles of D and 1 mole of E. In other words, using the exact coefficients in terms of moles will give you this delta H reaction. But you're often going to want to calculate how much heat was released, or in other cases absorbed, by a different amount. So you have to use this as a conversion factor. Okay, so what we can say is that negative 200 kilojoules per 2 moles of A. Or we can use any other substance we want to, or negative 200 kilojoules per 3 moles of D produced. So it could be negative 200 kilojoules per 2 moles of A reacted, or it could be for 3 moles of D produced, or any of the, in terms of any of the other substances, but it's for those certain amounts of, as written as the coefficients. Okay, so it refers to a specific balanced equation. That's the point. The numbers refer to a specific balanced equation. If we had twice as much, if we had 4 moles of A, we would have 400 kilojoules. Okay, whatever factor you multiply these by, you would multiply the delta H reaction by as well. Okay, so if 4 moles A react, the delta H would be negative 400 kilojoules. All right, and you can also look at what the reverse reaction would do. Okay, let's say you started with 3D and 1E and created the reactants. Okay, so if you do the reverse reaction, the products going to the reactants, the delta H for that is going to be the same magnitude but the opposite sign. So that would be a positive 200 kilojoules. So anytime you reverse a reaction, you'll get the opposite sign for the heat of reaction. All right, let's look at one example and then I'll have you try one. Let's look at a real example, generic. Okay, iron 3 oxide plus aluminum going to aluminum 3, well, just aluminum oxide and iron. And the delta H here is negative 849 kilojoules. This is known as a thermite reaction. It's a very exciting reaction to watch because it produces a lot of heat. 849 kilojoules is a lot of heat. And since it's negative, you know that's released. Okay, it's exothermic. It produces heat. So the question is, how much heat is released from the complete reaction of 42 grams of aluminum? We know this amount of heat is released when 2 moles of aluminum react, but we want to know for 42 grams, which may or may not be 2 moles. So we got to figure out what it would be. All right, so we take the amount of of grams of aluminum and convert it to moles. Okay, the molar mass of aluminum is 27. Okay, so that converts it to moles, and then we use this as a conversion factor, remembering it's for 2 moles of aluminum, because there's a 2 out here. So we say the amount that's released was 849 kilojoules per 2 moles of aluminum. So we will cancel the moles of aluminum, we'll cancel grams of aluminum. Oops. Don't do that. Cancel gram. I can't do that. Okay, never mind. Leave it there. Cancel the grams, and you'll get 660 kilojoules are released. Okay, and you may notice I did not put a negative sign on there, and that's because the question already asked how much is released. If it simply said, what is the heat change, then you would want to put a negative on there. But since it says the word released, that implies it was given off. It's a negative delta H. Okay, so you try this one, and I will work it. How much heat is produced from a reaction of 145 grams of tungsten using this reaction with this delta H? All right, so how much we started with? 145 grams of tungsten. Convert that to moles. 183.84 grams. And then use the heat amount. It's asking how much is produced, same thing as released. It's not saying absorbed. 1685 kilojoules, and that is per 2 moles of tungsten. And that gives you 665 kilojoules produced of heat. Okay, and again, if it was an endothermic reaction with a positive delta H, we would say the amount of heat we'd calculate would be the amount absorbed. So I will just put that in parentheses for endothermic reactions. We would talk about heat absorbed.